This is video 2 on rational functions. We're going to be looking at defining a rational function, finding its domain, vertical asymptotes, horizontal asymptote, any holes, and sketch. So let's get to it. Alright, just to review, a rational function is a function that is the ratio of two polynomials. For instance, if you'll look down here, this function, this rational function is the ratio or a fraction of two polynomial equations. So there's a polynomial in the numerator and a polynomial in the denominator. And if you'll remember, since this is a fraction, you cannot divide by 0. So any value that makes the denominator equal to 0 is undefined. Please get these notes. It pretty much restates it. Both of these things restate the same thing, but please get these notes down in your notebook. So here are some examples of rational equations. Here's some examples. So I have a cubic in the numerator and a quadratic in the denominator. This is a rational function. This one has a linear and then a quartic in the denominator. Also one like this, the top polynomial is just 1, which is a line. And then this one, the denominator is 1. So these could all be considered rational functions. Here are two examples of ones that are not rational. These are not rational. And then this gives you the reason here, but because of the square root, this is not a polynomial. It has to be a variable to a power. This one is itself a rational function. 1 over x is rational. So this whole thing is not rational because this is not a polynomial. The parent rational function is f of x equals 1 over x. And we're going to go ahead and graph this function. So I'm going to make a table, just a very simple table, the x value and f of x values. And we want to look at its behavior around 0. So I'm going to do the 5 parts. If I put a -2 in for x, this will be -1/2. This will be -1. If I put a 0, I will have 1 over 0, which is undefined. So the graph does not exist there. 1 over 1 is 1, 1 over 2 is 1/2. So if I go over here to this very, very small graph, what was I thinking? I'm going to go in and put just a couple things here. So -2, change colors, -2, -1/2 is here. -1, -1. There is nothing at 0. That's actually an asymptote at x equals 0. And then I have 1, 1, and 2, 1/2. And this is what the parent function of 1 over x looks like. It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. And it's in the graph of it, the basic parent function are in quadrants 1 and 3, but not 2 and 4. An example, though, however, if I were graphing the function f of x is -1 over x, remember that the negative out front is a reflection over the x-axis. And what that does to the rational graph, it does not change the asymptotes, but it changes the graph from the first and third to the second and the fourth. It would look more like this. Same asymptotes. So all the transformations that we've used with different functions apply to the rational function. You can still move it right, left, up, down. You can reflect it over the x-axis. You can actually reflect it over the y-axis, but that's not done as often because it's basically the same graph as reflecting it over the x, so there's really no reason to do that. So be sure you have this down. This is the basic shape. This is what you do. So if you have one that you're moving right, left, up, and down, this is how it starts. So be sure that you know some of these key points. Another graph that's very similar to this looks like, if I use the same function points here, then I have 1/2. I have 1 over 1 squared, which is 1. 0, of course, is undefined. This would be 1 over 0, so this is undefined. So there's an asymptote there. 1 over 1, 1 over 2 squared is 1/4, which means I got this one wrong, 1/4. Okay, so what you're seeing here is that it is impossible for f of x values to be negative. So there will be no graph in where y is negative, and that would be in this quadrant and this quadrant. So I still have an asymptote here at y equals 0. I have another asymptote at x equals 0. And my graph is going to be in the first and second quadrant. Okay, so on the 1 over x graph, the behavior, this is what 1 over x looks like, right? The behavior at x equals 0 says that as we get really, really close to the asymptote, this is going up, this is increasing. And as we get really close to this asymptote, the graph is decreasing. So in other words, at the vertical asymptote, they're going in the opposite direction. Now on this graph, the 1 over x squared, sometimes we call this, it blows up, because that's kind of what it looks like. It's blowing up at the asymptote. So here, as the graph gets closer and closer to the asymptote at y equals 0, it's going in the positive infinity direction. And if this one, it's going in the same direction, because this is a perfect square. So because this is a perfect square, that's what this graph does. And you can see it in relationship to the other graph. Now, without graphing, we can find the domain in any vertical asymptotes of each of these two rational functions. I know they're rational because it has a linear function in the numerator and a quadratic in the denominator on this first one right here. So what I want to do to find the domain of a polynomial is all reals. But because you cannot divide by 0, there are exclusions to the domain, and that is where the denominator is equal to 0. So I'm going to set the denominator equal to 0 and solve. So I have x squared is equal to 5. Remember, when you take the square root of something squared, you get 2 answers. So the domain of this function is going to be all reals except x cannot be plus or minus the square root of 5. So to find any so that's also where your vertical asymptotes will be. You have a vertical asymptote at this x equals the square root of 5 and x equals negative. There'll be 2 of them, 2 vertical asymptotes. So that limits your domain. It will be all reals except x cannot be plus or minus the square root of 5. To do that here, right, I'm going to set the denominator equal to 0. So I have x squared plus 5x plus 6 equals 0. To solve, I'm going to factor, and I'm going to do 2 and 3, since I have to add both of them, will be this. So x is going to be -2 and -3. So the domain of this function is all reals and x cannot be -2 or -3. Where are my vertical asymptotes? Asymptotes are lines. So the two equations of my vertical asymptotes are x equals -2 and x equals -3. Those are the equations of my vertical asymptotes, VA. Now, in order to determine a horizontal asymptote, if it has one, there are 3 possibilities. It doesn't have one at all. It has one, but it's at the original location, which is y equals 0, or it has been moved up and down some direction, and that would be this one. Okay, so here are the examples. And there are numerous ways to remember this. There's some bigger on BOB, Bot Bob something, I don't even know, I don't know that one exactly. The one that I remember I will tell you in class, but here are some examples and I want you to write these down. So the first possibility, what you do is you look at the highest power in the numerator and the denominator, the highest power. In fact, for a horizontal asymptote, you don't care what the rest looks like. For vertical, you set the denominator equal to 0 and solve. But that's not what we're doing here. We're looking for the horizontal asymptote. Okay? So the highest power in the denominator and the numerator. So looking at this here, I would pick x squared in the top and x in the bottom, and I would compare their exponents. This particular one, the bigger exponent is on the top. If the bigger exponent is on the top, it does not have a horizontal asymptote. I look on this one, and notice I've got dot, dot, dot here because it could have a big long string of things. The x to the fifth could have, 4 other terms. Don't care. For horizontal, I just look at the largest in the top and the bottom. It's bigger. The bigger number is in the denominator. So that means that the asymptote is at y equals 0, the x-axis. Okay? And then the third one, if I look at the two top ones, I notice that 3 and 3 are the same. The coefficient out here is 1. So if they're the same terms, you just take the coefficient numbers out from in front, so y is equal to 1/2. Okay, quickly, to put these two together, to find a vertical asymptote, you set the denominator equal to, that looks like demon, doesn't it? Denominator equal to 0. So I'm going to set 2x equal to 0 and x squared minus 25 equal to 0, which of course you could factor, or you could solve it the other way. I'm just going to factor it. So x is negative 5 and 5. X equals 0, so I've got 3 vertical asymptotes. I have a vertical asymptote at x equals 0, x equals negative 5, and x equals 5. It has 3 vertical asymptotes. For horizontal asymptote, I'm just going to write the highest power in the numerator, and then I'm going to have to multiply. So in the denominator, I'm going to get 2x to the third. Now I don't care about the rest of the denominator, I just want to look at the powers. I can see that the powers are the same, so I'm going to take the coefficients. So it would be y equals 2 over 2, which is 1. One other possibility is a hole in the graph. A hole in the graph would look like something like this, where I had the graph, but at x equals some number, there would not be a value there. It would be a hole, and that's how you would graph something like that. So I can see here a hole in the graph is going to be when, after you factor a polynomial on the top and the bottom, that there is something you could actually cancel, a form of 1. So this is a hole in the graph. It's not a vertical asymptote, it's an actual hole. So the hole would be located where x is equal to negative 3 on this particular one. And I don't know what the y value is, and there's no reason to plug it in. Just when you graph it, go to negative 3, find the graph, and put a circle there, put a hole in it. So like if there's this, I don't know what it is, but you could figure it out. This also has a vertical asymptote. The vertical asymptote is at x equals negative 5 with a hole at negative 3. And then what you would have for the top, for the horizontal asymptote, the top would be x squared. You're going to find the horizontal asymptote before you find the hole. So before you cancel. And so then the bottom would also be x squared, and so it's going to be a y equals 1. Here is the problem that I want you to work for homework in your composition notebook. Determine if there are any holes, vertical asymptotes, horizontal asymptotes, and x-intercepts. To find an x-intercept, you would set the numerator, you're going to set the numerator equal to 0. So for that, set the numerator equal to 0 and solve. A vertical asymptote, remember you have to find any holes before you can find a vertical asymptote. So we'll talk about this one in class. Please don't skip this part, and if I forget to ask about it, please ask about it in class. It's really important that you practice these and get these skills down. See you in class.